Hi everyone, it's Mr. Hamilton here. We're going to look at the rational function in front of us, and we're going to look at three different types of limits in this video. At the end of the video, you'll want to stay tuned because we're going to put it all together in a graph and show what each of the types of limits means. Now the first thing we generally want to do is we want to factor it if possible. And in this, it's definitely a case where we can factor it. We're going to take a common factor of x out of the numerator, and the denominator is a simple trinomial. So we're going to try to find two numbers that add to the middle term, -4, and multiply to the last term of 3. Now those two numbers, those two factors are -3 and -1. So because it's a simple trinomial, I can write it as x minus 3, x minus 1. Now you'll notice the x minus 1 is on top of an x minus 1. Those are going to cancel out, giving us a hole on the graph. Any factors that cancel are going to give us holes. In other words, those are going to be our point discontinuity limits. The factors that stay in the denominator are going to give us vertical asymptotes, or our infinite discontinuity limits. The end behavior limits are always looked at by looking out to positive infinity and negative infinity. So let's jump in. The first type of limit is a point discontinuity limit. We've already identified what those holes are, but let's go ahead and just recognize again that we have that as a factored form. And that's why I have it x approaching 1. Because as x approaches 1, what we're going to get is we're going to get a 0 over 0 in that fraction. And so what we can do is we can cancel those two out, and we can now look at the other part that still is left. And we can sub that limit when x approaches 1 in. So I have x over x minus 3, and I can sub that in now because that's not going to give me 0 over 0 anymore, and I get 1 over -2. What that means is there's going to be a hole at 1 and -1/2. So that's all there is to it with point discontinuity limits. Try to cancel it out, and then you can sub it in. Now infinite discontinuity limits, vertical asymptotes, is a little bit more tricky. In this particular case, what we can see again is we write that out in factored form, and I can cancel out the x minus 1s on the top and the bottom. We already know those are holes, and those are going to change the numerator and denominator in proportion to each other, so we don't need to worry about those. But what we now need to consider is, what if I sub 3 into that? What I'm left with. If I put 3 in the top, I'm going to get 3 over 3 minus 3, which is 3 over 0. So anytime you have it in the form something over 0, a number over 0, that is always going to give us a vertical asymptote. And what I have to do now is I have to approach it from both sides, because it's not going to exist right at 3. And so I have to come from the left side, and I have to come from the right side. So this limit as x approaches 3 minus, that means a number less than 3, an x value less than 3, so like 2.9. And this number 3 plus means a number a little bit bigger than 3, so something like 3.1. So let's start with the left side limit. So as x approaches 3 from the left, we can go ahead and substitute that 3 from the left in. It's thinking in your mind, it's like a 2.9. So 3 minus 3 from the left divided by 3 from the left minus 3. So it's as though we're putting 2.9 divided by 2.9 minus 3 into that fraction. Now keep in mind that all we can have for vertical asymptotes is we can only approach positive infinity or negative infinity. There's no other possibilities. So because of that, what we need to do is all we need to look at is what the sign of the numerator and denominator are, and then as you divide positives by positives or negatives, think about what sign that would be overall. Now, 3 minus, at 2.9 minus 3, that's a number a little bit less than 0. So that means it's a number that's negative. So we have a positive on the top, we have a negative on the bottom, and so that means it's going to approach negative infinity. So that is going to give me negative infinity. Now, I'm going to look at the right side. So I put a 3 plus in, a number a little bit bigger than 3, divided by a number a little bit bigger than 3 minus 3. Again, you could think of it being like 3.1. What's the sign on the top? What's the sign on the bottom? So the 3 plus is still on the top. On the bottom is a 0 plus. It's a number a little bit bigger than 0. So we have a positive over a positive. If that's the case, then we have a positive infinity limit. Remember, the only options were positive or negative infinity. So what does this mean? Well, it means that as I approach 3 from the right, it approaches infinity. The y value approaches infinity. And as I approach 3 from the left, which I did earlier, that y value is going to approach negative infinity. But what about the limit as x approaches 3? Because we looked at from both sides, but what about the limit in general? Well, it only exists if the limit from both sides approaches the same thing. And because it approaches negative infinity to one side and positive infinity to the other, we actually say that the limit as x approaches 3 does not exist. But yet it does mean something when we approach from both sides on the graph. But the limit, if it doesn't approach the same thing, does not exist at that value. And so that's how that works as far as how that's said. The last type of limit we have is end behavior limits. And so in this particular case, again, I'm going to write this out factored, and I'm going to just cancel out that factor that was common to both the numerator and denominator. We could keep it in there and it would work out the same way, but by canceling out those factors that are the same, it just simplifies our life, makes it a little easier to solve these. So I have the limit as x approaches infinity of x minus 3. Now here's the key. The key is this. We're going to divide all the terms in the numerator and denominator by the largest power of x that's in the denominator. Divide all the terms by the largest power of x in the denominator. So the largest power of x in the denominator right now is just x to the power of 1. So that means we're going to divide every single term, the x, and the negative 3, by x. So x over x in the numerator, x over x in the denominator, and then minus 3 over x. Now, x over x is just going to be equal to 1. And so we have that in two cases. So we get 1 over 1 minus, and the 3 over x we can't simplify. Now what I can do is I can look at this, and I notice the 1 over 1. Whatever I'm subtracting from it in the denominator, that 3 over x, that's going to make minor changes. But the 1 over 1, that forms my horizontal asymptote. So whatever those coefficients are that you get on the top and bottom, those numbers that don't have anything divided by x, that's how you determine what your horizontal asymptote is. So now what we want to determine is, well, okay, it approaches a horizontal asymptote at 1, but does it approach from above or from below? So I substitute in infinity into that equation. Well, what's 3 over infinity? Well, that's a number a little bit bigger than 0. And if I subtract that from 1 in the denominator, I go a number a little bit less than 1. Think about 1 minus 0.1. That gives me a number a little less than 1. Well, that means that I'm going to have a number a little bit bigger than 1, because if I have 1 over like 0.9 on the denominator, then I have something bigger than 1. Well, what does that mean? It means that it's going to come to the horizontal asymptote, y equals 1, from above it, positive above it. And that's occurring when the x value approaches infinity, because that's the limit that we just solved. Now let's do the other one, and we're going to pick this up from where I have it circled in green, because everything cancels out and simplifies the same way. So we get 1 over 1 minus 3 over x, but now we're doing negative infinity. So as I substitute negative infinity into this, 3 over negative infinity means I'm going to subtract from the 1 in the denominator. I'm going to subtract a number a little bit less than 0. So I'm going to subtract a negative number. So if I subtract a negative number, consider that number like negative 0.1, what that's going to do is it's going to make it add to the 1. So it's going to give me a number in the denominator that's bigger than 1. And if I take 1 that's in the numerator and I divide it by a number that's bigger than 1, I'm going to get a number slightly less than 1. It's smaller than 1. So what that means is I'm going to approach 1. I'm going to approach the y equals 1 from below, because it's less than 1. The minus means less than 1, means come from below, when x approaches negative infinity. So now let's put this all together and see how this looks when we put it all together on a graph. And we're going to answer the question, what does it all mean? So the first thing we did is we did the holes. And we determined that there was only one hole here, and that was when the x value approached 1, the y value approached negative 1/2. So there's a hole at 1, negative 1/2. And we can put that on our graph at positive 1 on the x-axis and negative 1/2 on the y-axis. We put a little hole there, a little circle. So it's like a dot that hasn't been filled in. The next thing we had was we had a limit at the vertical asymptote. And so the x approached 3 from the left, the 3 little with the minus sign, meant for 3 from the left. And we determined that that was negative infinity. So that as x approached 3 from the left, that the limit, whatever the limit equals, that's the y value, what it's approaching. So y was approaching negative infinity. So there's my vertical asymptote at 3. And as I come from the left side, it's going down to negative infinity. We found that the other side, when x approached 3 from the right, the 3 plus, that gave us an answer of infinity. It meant that y was approaching infinity. And so on the other side of that vertical asymptote, we're going to go ahead and draw an arrow that shows that going up to positive infinity. Now, end behavior limits. Well, we know that as we are going, as it says, the limit as x approached infinity, that meant that the y value is coming to our horizontal asymptote at 1 from above. So we go ahead and we draw our horizontal asymptote at 1. Here's our dotted line being drawn on the graph right there at a vertical value of 1, y equals 1. And so out on the right side where it approaches positive infinity, that means it's going to come from above. So there's my arrow there. So my horizontal asymptote is at y equals 1, and I'm coming from above on the right. On the other side, as x approached negative infinity, y was approaching 1 from below. The 1 minus meant y was approaching 1 from below. And so what we can do now is we can add the arrow for that on the graph. And that's going to be added on the left side of my graph. You can see it's coming from below. And I'm almost ready to graph it. There's two other things that are helpful to do to graph this. And so one of those is finding the x-intercept. The other is finding the y-intercept. The x-intercept occurs when y is 0. So I'm just going to go back to my factored form of this. And I'm going to substitute in 0 for y. Now, x minus 1 over x minus 1 canceled out. And so if you rearrange that by multiplying both sides by x minus 3, 0 times x minus 3 was just 0. So you get 0 is equal to x. In other words, the x-intercept was 0. Now, that's the origin. So you might be suspicious that that would also be the y-intercept. And if that's the case, you're right. But just to check it, we're going to substitute x equals 0 in now to find that y-intercept. And what you can see here happens is we get 0 over negative 3 times negative 1, which is 3. So 0 over 3 is just 0. And so what we can do is we can plot that x and y intercept on the graph. It happens to be the same point in this case. And then we join our arrows up together going through that x and y intercept and through the hole in this particular case. Now, you might wonder, okay, is the x and y intercept going to be similar distance from where those asymptotes meet? And it often will be, and it is in this case. And so I'm going to go over 3 and up 1 to just draw points in the top right corner, and then I'm going to join those arrows together as well. That right there, ladies and gentlemen, is the graph of that rational function that we started off with. And so there it is in its original form, x squared minus x over x squared minus 4x plus 3. If this was helpful, please like and subscribe. If you're looking at oblique asymptotes, there are situations where you don't just have a horizontal asymptote, but an oblique asymptote. And that occurs when the numerator is a higher degree than the denominator. If that's what you're looking at, check out the video on the right. For more videos all about advanced functions topics, check out the videos on the left. Thanks so much for watching.